Okay, so this little lesson here is about a little more practice with using kind of that scaling method, the idea of mole-to-mole ratios, and how we can use mole-to-mole ratios to tell us more about what's going on in a chemical reaction. So, number one thing to kind of keep in mind is that a chemical equation like this is a recipe. It's kind of like saying, I need some sugar and some butter and some flour, and I'm going to make chocolate chip cookies. And that's kind of what we've got going on here. We have a slightly different version of it here. We've got nitrogen and we've got hydrogen, and they'll be making ammonia. So that's basically our recipe that we've got. But just like with any recipe, one of the first things that we need to make sure that we do is to have actual units in our recipe. Because if I just say flour plus sugar plus butter, go, who knows what you're going to make, but it's probably not going to be cookies. So first thing that we need to do with any of our sort of chemical recipes like this, you have to make sure to start off by balancing the equation. So in this particular case, I notice that I've got two nitrogens over on this side. I've only got one nitrogen over here. So I'm going to use this as a way to balance my equation. I'm going to put a 2 over in this spot, and I'm going to put a 3 over here. Now my equation's balanced. So now I actually know the ratios of things that are involved. So these ratios here of this 1 to 3 to 2 ratio tells us something important. It could say 1 cup of flour and 3 cups of butter would make 2 dozen cookies. It doesn't, but you know what I'm saying. In this case, it means that we could have 1 nitrogen molecule and 3 hydrogen molecules gives us 2 ammonia molecules. It's one way to interpret this reaction. Not the most useful for us because we don't really do chemistry at the molecular level, us being giant human beings that we are. We tend to do chemistry on the molar level, and this is what you're going to hear me refer to this from now on, is that we've got 1 mole of nitrogen and 3 moles of hydrogen will end up producing 2 moles of ammonia. And that's kind of how we're going to talk about it, as a mole-to-mole-to-mole ratio for this. And again, when we're talking about mole-to-mole, it can be any pair of things. We could say 1 of these will react with 3 of those. We could say 1 nitrogen will produce 2 ammonia. Or we could say that if I had 2 ammonia that I would need 3 H2. So anyway, we can go from any spot to any other spot in the reaction through this chemical equation. So because it's a chemical recipe of some sorts, we can do things with this recipe like scale it up or scale it down for that matter. So let's say, for example, I wanted to double my recipe. I've got extra friends coming over and I need twice as much. Well, if I need twice as much, it's actually pretty straightforward. I'm just going to do this. Multiply everything by 2, right? So my new ratio would end up being a ratio of 2 of these to 6 of those would give me 4 of those. 2 N2s, 2 nitrogen moles, plus 6 moles of hydrogen would yield 4 moles of NH3. So again, it's just a matter of scaling it up. I could scale it up more. What if I've got a whole bunch of friends coming over, maybe instead? Maybe it's 10 of my sets of friends. I don't need just times 2. If I want to do it times 10 instead, same idea. Times 10, times 10. Wow, I can't even write today. Times 10, and times 10. If I want to do like that, then what would I get? Well, 1 mole times 10 would give me 10 moles of that. 3 moles of hydrogen times 10, 30 moles of that. 2 moles times 10 would give me 20 moles. In other words, it doesn't really matter what our multiplying factors are, whether it's 2 or 10 or 0.5 or 100, it still has the same basic ratio. And we can use this idea to kind of scale up or scale down our recipes. Again, if I wanted to do a half a mole or scale it down to a half of a recipe, I can do exactly the same thing. If I wanted to do it times a half, and then times a half, what would our final ones be here? Well, this would be a half of a mole. This would be a half of 3, 1.5 moles. And this would be a half of 2, 1 mole. So we can scale it up, we can scale it down. Doesn't matter in terms of that particular item. Okay, let's move on here, take a look at a little bit more of an extension on. Okay, so let's talk about scaling it a little bit further now. We're going to focus on kind of one particular element. I'm going to focus, for the purpose of what I'm doing here, I'm going to focus on nitrogen and tell me about how much of the other 2 things I need. So let's say I needed to do some funky methods. We know that this original ratio is a 1 to 3 to 2. But what if I needed some weird number like 22.5 moles of nitrogen? What would I need to do to figure out the moles of hydrogen or the moles of ammonia that were produced here? Well, the good news is, it's actually not that hard. What was my multiplying factor as I went from here to here? Well, I multiplied it by 22.5. So I'd do the same thing here. times 22.5. The numbers don't have to be easy, and they certainly don't have to be pretty in order to make this work. By the way, 22.5 times 3 is 67.5 moles of H2 would be needed, and 22.5 times 2 ends up being 45 moles of NH3. So this is all good. It doesn't really matter what the scaling factor is. We just need to take a look at how those ratios work. How about if I did this one instead? 3.04 moles of ammonia is or nitrogen is what I happen to have. Well, I'll do the exact same process. You're still doing everything else, times 3.04 times 3.04. You're doing this to every single one of them. So 3 times 3.04, if I can get my calculator out, I know you guys can't see me doing it, 3.04, happens to be 9.12. So that would be our new ratio. If I had 3.04 moles of nitrogen, I would need 9.12 moles of hydrogen to make it react. And that would also mean in terms of production, I would get 3.04 times 2, which is 6.08. 8, there we go, moles of this stuff. Again, everything multiplied by the same factor. It doesn't matter whether it's a big number or a little number. If I had 0.27, some random weird small number like that, how did I get to this? Well, I multiplied the original ratio, which was 1 times 0.27. I'm going to do that the same thing with all of these and get every one of them to 0.27. So 0.27 times our 3 for hydrogen gives us a 0.81, and then 0.27 times 2 for ammonia gives us a 0.54. Like that. So again, doesn't matter what the multiplying factor is. You can have multiplying factors that are big factors like that, you know, kind of weird random numbers, or they can be small factors. The same idea is that whatever you do to the first one, you have to do all the way across to all three. So moving on. What if we're starting to work from weird numbers? This has all been really nice because I was starting here, and because that's had got a ratio of 1 in front of it, it makes it actually really easy to do all the other math. What if we start with a different value? And I'm going to start here. Let's say we have 12 moles of this. How do we figure out how do we deal with the other parts? It's still the same idea. It just isn't the same multiplying by 1. I need to figure out what did I do to get from 3 to 12. In this case, I happen to know it was times 4. It's a little bit easier to do it because I can kind of see, well, 3 times something equals 12. Well, all right, figure out what it is. What I really did was this. 12 divided by 3 equals 4. That's how I figured out what my multiplying factor was. I took the number that I was given and I divided it by the number that was in the ratio to figure out what my scale factor was, times 4. So that's what I'm going to do to all my other ones at this point. It's the same idea. So what would I get? This would be a ratio of the nitrogen times 4 would give me 4, would react with 12 moles of hydrogen right here, 4 of these, 12 moles of these. And then for the last one, I would do 2 times 4 to give me the amount of product that I would get, which would be 8. So again, not too crazy in terms of how you're doing these, as long as you remember what it is that the math that you're actually doing underneath. And that can be the hard part, is actually remembering what kind of math you're doing underneath. So next part. Let's say, okay, I'm going to get rid of all these guys. What if we're actually doing some other crazy number? Let's say I've only got, well, my ratio is 1 to 2, 3 to 2. What if I've got 1 mole of H2? What did I have to do in terms of my multiplier to get from 3 to 1? Well, in this case, I divided it by 3, right? I did, the conversion factor is this, the number that's in the problem, 1, divided by the ratio number, which is 3. And I get 0.33, right? Repeating. So that's my multiplier that I'm going to use on everything else. So this one over here is going to be 2 times 0.33. This one is going to be 1 times 0.33. So our answers here are total ratios. If I start with 1 mole here, it's going to be 0.33 here, and it's going to be 0.66 here. It doesn't really matter, again, what the ratios are. It's got to be some sort of divider, basically, to kind of figure out how this works. So this to me is kind of a pain in the butt. So what I really prefer to do is, rather than trying to figure out the dividing and all that kind of stuff, you know me, I love the Wunderfraction. And I would much rather do this with a Wunderfraction than try to scale everything up. Especially like to do this because when we get into later types of problems where we're building on this as a central step, it's a lot easier to kind of have more complex problems with a wonder fraction rather than dealing with it step by step. So I'm going to show you how to set up a wonder fraction here. With wonder fractions, the key idea here is you always start with what you know, what you're given. Like in this problem, I'm giving 7.5 moles. And how do I convert it to NH3 and N2? So I'm going to set up a little wonder fraction. I'm going to start over here. 7.5 moles of H2. Again, I'm starting with what I'm given, which is the quantity of that particular chemical. Next thing I'm going to do is I'm going to draw my little wonder fraction lines. There we go. And now this step over here is going to be a conversion. MOL to MOL. What I'm trying to convert to and from is kind of important. I'm trying to get rid of hydrogen, so this is going to be H2 down here. And let's say for this first part of the problem, I'm going to convert it to N2. So on the top is going to have to be N2. Now what do I use for my conversions? What goes here? Again, this is just a conversion factor. Well, our balanced equation is a conversion factor. 1N2 reacts with 3H2, and those are the values that I put right in there directly in the problem. 1 mole of N2 reacts with 3 moles of H2. Those are from the balanced chemical equation. And now I could actually just do my equal sign and figure out what it is. This would end up being, if I want to math it out, 7.5 divided by 3. This actually tells me, I don't have to think about it too hard, what the math is that I needed to do. So 7.5 divided by 3, by the way, is 2.5 moles of N2. What about NH3? Well, you can kind of start it off the same way. What if I want to figure out, all right, starting here, how much NH3 can I make? Start it off with what you know. So again, I'm going to do a second little wonder fraction down below here. 7.5 moles of H2, because that's what I was given. It's my little wonder fraction line. Now in this particular case, I'm going to go from H2 to NH3 to figure out what that would be. Again, I'm going to do the same process like we've done before. Focus on the steps that you're working on, crossing it down. So my moles of H2 is going to be down here. And now in this case, I'm going to go to the product, moles of NH3. Why did I go to that one? Because that's the one we were talking about before, so I'm going to use that one. Okay, what's our ratio? Well, we're going from H2 to NH3. Here's our ratio. That's our recipe. 3 of these are needed to make 2 of those, and that goes directly into your formula. So 3 H2s, there's my 3, is needed to make 2 NH3s. And you can see why the math here is a little bit easier to do sometimes. When we do the math out on this, again, multiply across the top, 7.5 times 2, divided by the numbers that's on the bottom. So 7.5 times 2, let's see, times 2, I'm using my calculator, divided by 3, is exactly 5. I knew that. Why am I doing this? Is 5 moles of NH3. So again, this is the wonder fraction method. You can scale it up and scale it down, kind of like what we were talking about earlier, but I really prefer to use this method instead. Instead of trying to figure out what the scale is, I can just use the balanced coefficients from the equation, and that becomes my conversion. To me, I think that's easier. You may have a different opinion than me. You're welcome to it. Hopefully that works for you. All right? Last bit. All right, this one is your turn. Let's see if you can do one of these problems basically from start to finish on your own. It's starting with the same exact reaction, nitrogen gas plus 3 hydrogen gases produce 2 ammonia molecules. If you want to produce 0.045 moles of ammonia, there it is, how much of each reactant do I need? So this is going to be a 2-part problem. You need to do one for the first reaction and then do a second similar one for the second reactant. Don't try to do this all in one problem. So this would be a really good time for you to hit pause for a second, see if you can work it out on a piece of scratch paper, and then move on. And I'm going to come along and do it here in just a second. So hit pause now. 3, 2, 1. And here we go with the solution for it. So 0.045 moles of ammonia. Again, every time we do these problems, you start with what you know. 0.045 moles of NH3. Okay, again, because that's what it's given to me in the problem, moles of ammonia. Next part is I'm going to draw my little conversion factor here, my little wonder fraction, yeah. And then I'm going to use my mole-to-mole ratio. So NH3 is on the top. Since I'm in moles of NH3 needs to go on the bottom, MOLNH3. And I want to convert it to each reactant. So for this case, it doesn't really matter which one I do first. I'm going to do the one that's kind of first in the equation. I'll do N2 just because it happens to be the first one, but I could have done the other one first. So moles of N2. And if I carry all this stuff out, I have to use my mole-to-mole ratio. So my mole-to-mole ratio for NH3 to N2 is 2 NH3s to 1 N2. So I've got 2 moles of NH3 is going to be produced from 1 mole of N2. And now at this point, it's a matter of doing the conversion. So I would do 0.045 divided by 2, which I believe, I have not done this in my head, 225, I guess. I'm doing it in my head, so if I did it wrong, yeah, you can be mad at me later. So moles of N2. I'm going to do the same process for the other reactant. 0.045 moles of NH3. Note how when I do these, even though my handwriting is terrible, I always make sure to include my units and my labels. So units I mean like moles, and labels I mean like the chemical, because it gets really easy to get confused when you're doing these problems if you just got a bunch of numbers flying around. So put all those pieces in there. Alright, next step, it's got to carry on down, so it's going to be moles of NH3, because I'm going to cancel those out. My other reactant is H2, so it's going to be moles of H2. It's always moles to moles, so make sure that you put that in there. And then for this part, I'm going to be taking a look again at my mole-to-mole ratio. For NH3, it's 2, and I would need 3 moles of H2 to deal with that. So I'm going to put my mole-to-mole ratio. 2 NH3s is going to produce 3 N2s. H2, sorry. So I'm going to go grab my calculator because I have no idea what 0.045 is. So math-wise, what I'm going to do here, again, multiply across the top. So it's these two, and then divide by the 2 on the bottom. So 0.045 times 3 equals divided by 2 equals. And I get a number, oh, my calculator says 0.0675 moles of H2. So there you have it. Some practice on doing some of these mole-to-mole reaction, kind of review on doing our wonder fraction steps. I hope you've enjoyed it and kind of got you kind of mentally warmed back up with how to do some of these things. See you in the next one.